Start by thanking Let me start by thanking the organizers for the kind invitation. It's a pleasure to be here at this workshop, and I'll be talking about joint work together with Aaron Held on a principled parameterized approach to black holes beyond GR, and in particular the images. And so the approach I will be discussing is trying to sort of combine the best of both worlds from a parameterized and very general approach to black holes on the one side, and a more principled approach sort of coming from fundamental physics and theories beyond GR on the other side. So this approach is trying to take sort of the best of both and combine them and understand which fundamental principles could potentially lead to which imprints in black hole images, so that by observing black hole images in the future with higher precision, we might be able to infer back on some general fundamental physics principles. So that's the spirit of the approach. So let me delve in. So to set the stage, this is of course all in the context of sort of these three seminal results that we've heard a lot about in this meeting: post-Newtonian orbits around a supermassive black hole, the gravitational wave signals from binary merges, and also the first shadow image. And the question that I'm concerned with is whether these are really the black holes from general relativity. And of course, by that question, I don't mean to imply that any deviations from general relativity have already been observed. In contrast, general relativity so far provides a really excellent fit to the data. So there are currently no observational indications for deviations from GR. But on the other hand, coming from a fundamental perspective, we already know that the answer to that question has to be no, because black holes in GR are simply not truly consistent objects. They do harbor a curvature singularity, signaling the breakdown of GR. And that actually means that we don't understand the true nature of the objects that we are observing here. And so I will be interested in understanding how to explore the true nature of black holes and how to sort of leverage these various points of observational access to learn about the true nature of these objects. And so from the point of view that I come from, there are sort of two relevant questions here. The one is whether in this particular set of observations, we would expect deviations from GR to be sizable or large, or whether we expect them to be completely tiny. And the second relevant question is, what input do we need coming from a fundamental theory perspective in order to test deviations from GR? And so on these two dimensions, the post-Newtonian orbits are of course don't appear to be the most promising testing field, because here we would expect that because we're in a post-Newtonian and not yet the full-on sort of strong gravity regime, the deviations are expected to be very, very small. On the other hand, we don't need that much theory input. Because we don't need a full dynamics beyond GR. Here we actually just need the metric of the central objects, in which we can then calculate the trajectories of these sort of test masses. However, this type of observation can actually become much more important in combination with EHT observations, and I will be coming back to this point later in the talk. Then the situation is in some sense completely different for LIGO, in the sense that here we're really in a full-on strong gravity regime. So we do expect that deviations from GR could be detectable. And of course, when I write detectable here, I'm really taking a very optimistic point of view. On the other hand, this is a testing ground that is also, as has been emphasized in a number of talks in this conference, difficult to access, because here one really needs dynamics beyond GR, because we are really in a full-on dynamical regime of gravity. And controlling dynamics beyond GR, in particular, those types of dynamics that are of interest coming from a fundamental physics perspective, that's a big challenge. And that is something that hasn't yet satisfactorily been addressed. And so from where I come from, the Event Horizon Telescope is in some sense a bit of a golden opportunity, because we are still in a strong field regime, so deviations could potentially be detectable, but also we need less input from a fundamental physics point of view, because the thing that we need is just a metric beyond GR in which we can then follow the null geodesics. We don't yet need at that stage the dynamics beyond GR. And so for this reason, the main focus of this talk in the latter part will be how to connect metrics beyond GR, how to connect those to shadow observations. So therefore, I'm interested in shadows of regular black holes. And so for the talk here, I'm taking the point of view that whatever object we are replacing GR black holes with, it should be an object that is everywhere regular, so that doesn't have any curvature singularities. And of course, there is a vast literature on that topic, and apologies for not including any references in here. There's just overall way too much to put in here. But the main approaches to black hole shadows beyond GR actually fall into two main categories. On the one hand, there is what I will be calling the parameterized approach. That approach tries to be as agnostic as possible, and in a theory agnostic way parameterize all possible deviations of the metric from Kerr, and Luciano, of course, has been talking about that yesterday. On the one hand, of course, this is attractive because of its generality. On the other hand, that very generality also has the drawback that there's a certain disconnect from fundamental theory. Because imagine that you would be able to measure a bunch of deviations of metric coefficients from the Kerr metric. What exactly does that tell you about the fundamental physics principles that metric could potentially come from? So here there's a bit of a disconnect. And so then, of course, you can also, as we also heard from Luciano, sort of take the opposite approach, which I'll be calling the principled approach, where you actually start from a fundamental theory and you calculate the black hole metric and then the black hole shadow in that theory. And of course, you can compare that to observations, but then to cover the full theory space beyond GR, you would actually have to do that in each conceivable theory beyond GR. And that, for practical purposes, of course, is quite difficult to achieve. But also here we have to keep in mind that what observations like the EHT actually can offer us is always finite resolution. And so we don't actually need all of that information that we would get from this sort of full scope, or full sort of review of theory space. And so therefore, I think a useful approach to take is to try to combine the best of what both of these approaches have to offer and work within a principled parameterized approach. What I mean by that is we keep some of the generality of a parameterized approach and work with families of black hole metrics. But on the other hand, we also take some of the fundamental physics of the principled approach into account, and we include these general principles in developing particular black hole metrics. And so we are somewhere in between, where we have families of metrics, so not just specific models, but families of models, but these families do have input from a fundamental physics perspective. So that's the general idea here. And so then let me delve right in and tell you a little bit about the principles that we've put in to construct a particular family of black hole metrics, and then how these specific principles that we've put in, how they actually lead to particular image features for black hole shadows. So the four principles that we've used are for a family of spinning metrics. And I'm just emphasizing the spinning here because that, of course, from an astrophysical point of view is a really crucial ingredient, but it is something that is sometimes neglected in these developments of regular black holes. A lot of work focuses on spherical symmetry. However, as you will see, the spinning case actually has a number of quite exciting intricacies to it. And so I'll be focusing on spinning metrics here. I will actually be describing the black hole spacetime by a metric. And for some of you, that might sound like a completely obvious thing to do. But when you think about it from a sort of very deep, potentially even quantum gravity point of view, then it's not at all clear that spacetime down to the sort of very vicinity of the spacetime of the curvature singularity, that can still be described as a continuous manifold with a metric, and that those concepts don't break down. So here I will be assuming that you can actually describe a black hole completely by a metric. Then the second key assumption will be the regularity principle. So space-time curvature is finite. All of the curvature invariants stay finite everywhere. And then the third input, the third principle, is already something that connects to observations, because of course we want those objects to be asymptotically flat, and in the faraway limit, we want to recover the Newtonian potential, as well as potentially sort of first post-Newtonian corrections, which are constrained from observations. So we want to recover that correctly, and that constrains the spacetimes. And spinning and non-spinning metrics based on these three principles have been constructed in the literature. There's actually quite a vast literature by now that constructs different metrics. So the one thing that is really new in what we have been doing is that we also include a locality principle. And that locality principle, that is what is very much motivated from a fundamental physics perspective, or even from a sort of quantum gravitational perspective on gravity. And that locality principle essentially tells you how the deviations from the Kerr metric look like. And I will explain that in a little bit more detail. So in fact, what I will do now is I will tell you a little bit more details about each of these four principles and how they lead to a particular family of metrics that we then explore and where we calculate what their shadows look like. So the first principle, as I said, was that the black hole spacetime has to be described by a metric. And so our starting point is actually the Kerr metric. So this is nothing but the classical Kerr line element. And I've written it in ingoing Kerr coordinates here. And I'd just like to stress that the choice of coordinates is actually something that turned out to be quite important when we were constructing these spacetimes beyond GR, because if you have coordinates that have a coordinate singularity at the horizon, such as, for instance, Boyer-Lindquist coordinates, then these coordinate singularities, so these divergences and metric elements, they have to cancel in a very delicate way once you look at curvature and variance like the Kretschmann scalar. And now if you start to modify these metric elements away from their Kerr form, then generic modifications very quickly promote this coordinate singularity to a curvature singularity because this delicate cancellation doesn't work out anymore. And so therefore, what we did instead was, as shown here, to work in horizon penetrating coordinates and to develop this family of metrics beyond GR in horizon penetrating coordinates, because that evades this issue. So then the second point is that spacetime has to be everywhere regular. And this is where we now start to change our metric so that spacetime becomes regular. And what do we have to do in order to achieve that? Well, if you think about it from a physical point of view, then in order for curvature singularities to disappear, gravity has to be sufficiently weakened in the center of a black hole. And that can be achieved if you promote the mass parameter to a space-time dependent function. And if you demand that that function approaches zero fast enough as you approach the location of the classical curvature singularity, which is of course at r equal to 0. And in the spinning case, it lies in the equatorial plane. So this chi here, that is the cosine of the polar angle. And so chi equals 0 corresponds to the equatorial plane. So this is the location of the Kerr ring-like singularity. And sending that mass function to 0 fast enough allows you to lift that singularity and achieve a regular black hole. The second constraint on this mass function then follows from requiring the Newtonian limit. So for r going to infinity, this mass function just has to approach the classical mass parameter. And now this mass function still has a lot of freedom. And this is where this fourth principle, the locality principle, comes in. So let me explain the locality principle in a little bit more detail. Sort of the background of the locality principle is really thinking about local field theories, or thinking in an effective field theory way about theories beyond GR. So in an effective field theory point of view, you would say that deviations from GR are set in at large curvature scales. So the effective equations of motion are GR plus some higher curvature corrections. And what that means is that whenever you look at a region of spacetime with low curvature, then the Einstein equations are approximately correct, and therefore Kerr will be an approximate solution. Whereas if you look at regions within the Kerr solution where spacetime curvature becomes large, then these higher order corrections would kick in and to mean that the solution to the full theory will deviate significantly from Kerr. And so that means that the size of the deviations from the Kerr metric, so how much we deform away from the Kerr metric, that should be set by the size of the local curvature. So that's the locality principle. It says that the local value of the curvature determines how much you deviate from Kerr. Now this sounds very nice, and you can straightforwardly implement it in spherical symmetry, because in spherical symmetry, there is actually only one independent curvature invariant that is available. In the case of a spinning black hole, this is where the intricacies start. So in the case of a spinning black hole, curvature invariants show a much more interesting behavior. For instance, if you take a look at the Kretschmann scalar, which I've shown here as a function of r, and again chi being the cosine of the polar angle, as you then move from the North Pole to the equator to the South Pole at a constant value of the radius, you can see that the Kretschmann scalar changes its sign. So that is the first challenge. How do you deal with these changes in sign, and how do you deal with the fact that the curvature, even arbitrarily close to the singularity, that this curvature invariant can vanish there? Well, it becomes even a little bit more complicated because the Kretschmann scalar isn't the only independent invariant for the Kerr spacetime. There is a second independent invariant. And what I've done here in this plot is I'm showing actually 4 of the curvature invariants, their absolute values. And you can see that various of them go to 0 at different locations in the spacetime. And so the way that we interpret this locality principle here is to say that, first of all, the sign of the curvature invariant is irrelevant. So whether the curvature becomes large and positive, or whether its absolute value becomes large, but it is very negative, that doesn't matter for those corrections here to become important. And also, you should imagine that here there is a bunch of different operators, different curvature invariants, or different variations of curvature invariants. And wherever any of those is large, do you expect that the deviations from GR are large? And so therefore, what we then do is to construct an envelope function of the polynomially independent Riemann invariants for the Kerr spacetime. And that is what sets our scale. And that actually takes a surprising simple form. So this is this K, and this is what it looks like in those coordinates. And so we say that the general mass function that parameterizes the deviation from Kerr and that parameterizes how gravity weakens as you go to the core of that object, that mass function actually just depends on this curvature invariance times L to the 4. So this L and P, that stands for new physics. That is the scale of new physics. And so under the locality principle, this very general mass function that you could have vary in arbitrary ways becomes particularly simple and only depends on this sort of local size of curvature invariance. And then, of course, this mass function satisfies sort of the limiting behavior that it vanishes where the curvature becomes large, so down here, and then it approaches a constant where the curvature becomes small, so up here. And of course, in the literature, there are already a number of different mass functions that were developed in the spherically symmetric context. So Dymnikova-Hayward and Simpson-Visser are sort of 3 paradigmatic cases. And these mass functions, these shapes, can be used then in the spherically symmetric case as sort of 3 paradigmatic examples for this family of spacetimes. And so in summary, what that construction then looks like is that we get this family of spacetimes. It's a family because you can choose these different mass functions according to these different shapes. And then each of this mass function, so each of the sort of metrics within that family of spacetimes, that comes with 1 free parameter, namely the new physics scale, which determines at what value of the curvature the deviations set in. And what you see here is a sort of illustration that shows you how much you deviate from GR and how much gravity weakens. So this is just the form of this mass function. Out here, it essentially approaches 1 or its classical value. And then as you move towards r equals 0 in the equatorial plane, this is where it drops off fastest, whereas outside of the equatorial plane, it doesn't even have to go to 0 for the curvature to become regular everywhere. So this is the family of spinning metrics, of regular spinning black holes. And of course, what we are really interested in now is understanding how these could potentially give rise to observational imprints. And so the first thing to note in this context is that regular black holes are more compact than their classical counterparts, which is of course something that has been observed quite often in the literature. The physical reason behind that is simply that to resolve the singularity, gravity needs to be weakened. And so if you think about the horizon as the location where sort of light cones tilt so that you don't have any outgoing null geodesics, then at the location where you have the classical horizon, so where you have a horizon in GR, the mass function here has already decreased to be lower than the classical value, which means that the gravitational pull in the regular case is somewhat lower, which means that at that location, the light cones are not yet fully tilted. And so you need to move a little further inwards in order to reach the horizon in the regular case. And so this is what you also see in this illustration. This is the radial horizon coordinate. It's for a particular value of the spin, I believe 0.25. And then as you increase the new physics scale, so as the new physics sets in further and further outside, the horizon moves further and further inwards. And you can also see that the horizon is no longer spherically symmetric. In Kerr, it's very spherically symmetric. In this regular case, it has this little dent, and that will be a crucial feature that I will be coming back to later. But first of all, in this point that the regular black holes are more compact, there are two crucial questions, namely whether this result is actually generic or whether that's somehow an accident of a particular choice of mass function. And secondly, whether it's something that could potentially be observed. And the answer is that the result is generic under one additional assumption, namely a simplicity assumption. And that simplicity assumption is the assumption that the new physics comes with one single scale and there aren't any additional scales in the game. So if the new physics comes with just one scale, then what that scale does is it determines at which point the mass function transitions from its one limiting behavior to its other limiting behavior. And because it simply transitions from one to the other behavior, the mass function is actually everywhere smaller than one, which means that everywhere, in particular also at the location of the classical horizon, gravity is slightly weaker in the case of the regular black hole, which means the horizon moves inwards. If you wanted to circumvent that result, you would have to build a mass function that goes above one at some location, so that gravity is locally stronger in that point. So in this way, you could push the horizon outwards. But if you do that, then there is no way of doing that without the mass function having a second sort of special scale, namely a second transition scale. And so under a simplicity assumption where we are saying new physics comes with one single scale and no more scales, this behavior cannot occur. And therefore, this result that the horizon moves inwards appears to be pretty generic, at least in the spherically symmetric case. So then is this something that could be observed? And this is where the combination of post-Newtonian orbits and the Event Horizon Telescope comes in, because effectively what these measurements are determination of the black hole mass at different distances in the EHT, the sort of effective mass at near horizon scales, and in this case, the effective mass at something like 1,000 or more Schwarzschild radii. And so therefore, the effective mass that is determined here is expected to be larger. You're much closer to this regime where the mass function just has approached its classical value. Whereas here, you're somewhere in the regime where the mass function has started to decrease. And so you're expecting the mass to be smaller. Now, how large the effect is, that of course depends on the new physics scale. And it also depends to some extent on the mass function. And so you can then start to constrain specific mass functions and new physics scales. And we have tried a first attempt at that in a context that is motivated by asymptotically safe gravity. So what I will do now is move on more to analyze images in a bit more detail. And in particular, what I've done here is I've talked about what the imprints of regularity are on sort of images or observations. But I now want to in particular tell you what the imprints of the locality principle are on observations. So the locality principle results in a dent in the horizon in the spinning case. And the reason is that, as I've just told you, this regularization of the space-time results in an increase of compactness. And in the locality principle, the effects of the new physics are largest wherever the classical curvature was largest. And in the case of Kerr, the classical curvature is largest in the equatorial plane, which means that as you move inwards to smaller radii, the strongest effect, so the strongest compactification of the object occurs in the equatorial plane, whereas if you move towards different angles, the effect is lower. And so therefore, this increase in compactness is most pronounced in the equatorial plane. And so therefore, the horizon is pushed inwards most in the equatorial plane and least at the poles. And so that leads to a horizon that is no longer spherically symmetric, but that features this dent. And then since the horizon has a dent, this is actually something that is then also visible in the null geodesics that orbit around the black hole. So what I'm showing you here is the result of just tracing null geodesics through a regular black hole spacetime, where we've also put in an accretion disk, but we've not actually fully modeled that accretion disk. We've just put in a density profile by hand and given it a certain emissivity. And so what you see here is then, if you look at the prograde side of the shadow, if you sort of squint very, very hard, then you can see that a similar sort of small dent, sort of inwards dent, is visible here. And I'll be showing you zoomed in pictures more, but you can sort of already see, if you sort of trace the boundary of the shadow, that it follows a line that moves slightly inwards, that follows a slight dent. And so this dent follows directly because we have this locality principle that the modifications follow the value of the local curvature. And so therefore, if you look at a slightly modified case, which is also explored quite a lot in the literature, where the mass function is just depending on the radius, and you get that generically if you look at Newman-Janus upgrades of spherically symmetric regular black holes. For these cases, which don't satisfy our locality principle, so that you can think of those as non-local modifications, the horizon remains spherically symmetric, and therefore, if you compare the two images, you can clearly see there is no such dent in the shadow. So let me now move on and show you a few more images and elaborate on these imprints of regularity and locality a little more. So the first will be showing you the effect that I've talked about, namely the increased compactness now on a full image. And so here I'm comparing Kerr and then a regular black hole, where we've adjusted the mass parameters so that the retrograde shadow boundary here lies at the same location. And then this little gray box in the images also lies at the same location. And then you can see that the shadow boundary in Kerr is closer to the left side of the box, whereas in the regular case, the shadow boundary has moved inwards. So that's this increased compactification, and it is more pronounced on the prograde side of the shadow, because this is where geodesics are pulled closer towards the black hole horizon because of frame dragging. And so they feel more of this effect of increased compactness. And so there is this, as a first signature of regularity, there is the shift of the prograde shadow boundary. A second consequence of regularity is that image features are stretched. And to explain that, I will now show you just parts of that image which are within that box here. And what you can see if you zoom in there is that the shadow boundary is located on the inside here, but then stacked close to the shadow boundary are the so-called light rings. So they are generated by geodesics that orbit the black hole an integer number of times. So if they orbit once, they end up somewhere here in the image plane. If they orbit twice, they end up further inwards, and so on and so forth. So you get this exponentially stacked collection of light rings that approach the shadow boundary. And the further inwards you go, the stronger the effect of the weakened gravity that leads to the regularization. And that is this, and this effect of the weakened gravity is what leads to an increase in compactness. And so the further inwards you go, the stronger the increase in compactness, and therefore the innermost light rings are pulled further inwards. The outermost, they don't actually feel much of an effect of the regularization. And that actually means that these image features, so these rings, they are stretched relative to each other in the regular case. And I think it's actually a nice coincidence that the regular case is actually something where you need a little bit less resolution to see it than you would actually need in order to resolve these light rings in the case of Kerr. So both of these are image features that are tied to regularity. Now let's talk about the locality principle. So this is tied to this dent in the horizon, and that actually leads to cusps in the shadow boundary that you see if you zoom in quite a lot. So what you see in the shadow boundary, first of all, is also a dent. But then you also see these cusps as you move around here. And to understand why these cusps occur, we have to understand the behavior of the null geodesics that arrive in these different locations. What these null geodesics do, if we trace them back towards the black hole, is that they not just orbit the black hole in one polar angle, but they actually oscillate in the polar angle while they orbit around the black hole. And this is what you can see here. So in this image location, if you trace the null geodesic back, it oscillates in this whole range in the polar angle as it moves around the black hole. And then there's a point here where there is a transition to a much smaller range in polar angle. And then if you look at the effective geometry that these null geodesics probe, then because the horizon is no longer spherically symmetric, depending on this angle range that they probe, they see sort of effective objects of different radius. And so as you transition between these different ranges in the polar angle, you develop cusps in the image. And then as the final imprint of the locality principle of the dent, there is a broken reflection symmetry. If you go away from inclinations where you sort of just look at the black hole with its spin axis at 90 degrees. And this breaking of the reflection symmetry, you can understand that already in a geometrics optics approximation by comparing a spherically symmetric object like a Kerr horizon to this object that has a dent like the horizon in our regular case. So here it's a little overpronounced. This is not really how large the dent really is, but just to sort of show you what happens. And now, of course, if you tilt these objects and you go to different inclinations, so if you're not observing with 90 degrees, but with a different inclination, you can already see in this geometric optics analogy that the image will no longer be spherically symmetric, will no longer be reflection symmetric around the equatorial plane. And this is exactly what you see in these shadow boundaries here at different inclinations. Of course, the effect here is really, really tiny, so you would need quite a bit of resolution to see that. So in summary, what all of this allows us to do is to get access to this new physics scale, because the size of the effects here, of course, depend on the new physics scale. And of course, we can come with theoretical expectations of what the new physics scale could be. So for instance, we could argue that if the new physics is quantum gravity, that should be the Planck scale. On the other hand, in this very conference, we have heard talks that because of information loss, quantum gravity effects in black holes need to manifest themselves at much larger scales. So theoretically, we can argue different points of view. We don't really know. The great thing about the observations is that we can actually now start to put observational constraints. We don't need to put in our theoretical biases on that scale. We can actually just go and try to measure or constrain it. And let me use the remaining 5 minutes or so to
3 plus 5.
Okay, 3 plus 5. Okay, excellent. So let me use the 3 minutes to talk a little bit about consequences of the specific choice of mass function, because you could wonder in what I've been showing you here, whether that is sort of specific for this mass function or whether that's more general. And to do that, we actually compared a number of cases. So here I'm showing you different inclinations, and the left column that is Kerr. And then all of these 3 black holes are regular cases, but one is a mass function that does not satisfy the locality principle, and the other 2 are examples that do satisfy the locality principle. And as you go through these images, you see that 2 consequences from regularity, namely the shift of the prograde shadow boundary and the relative stretching of image features, that occurs in all of these 3 cases. So we can conjecture that that is really a generic consequence of regularity. Whereas cusps and broken reflection symmetry, this is something that you see only in those images where the locality principle is also satisfied. And so this leads us to conjecture that these specific principles, namely regularity, and on the other hand, locality, that they could be connected to relatively generic features in the images. And that, of course, then allows you to, on the other hand, start looking for such image features and thereby learn something about the potentially underlying fundamental physics. And so that brings me to my summary. So what I try to advocate here is a sort of middle ground between a very general approach to black holes and their images, a parameterized approach, and on the other hand, a fundamental physics approach where you work within specific theories. I've advocated that it would be very useful to develop a principled parameterized approach where we can learn how certain fundamental physics principles lead to particular image imprints, so that we can then look for these in the images and therefore thereby infer back on sort of classes of fundamental theories. And I've given you these two examples of regularity and locality, what they lead to in the metrics, and then what they lead to in the images. And so just to conclude, let me advertise a little bit that in just 2 weeks, there's the next virtual workshop on black holes, which focuses more specifically on actually just regular black holes and quantum gravity and beyond, and their connection to observations. So if you're interested in attending, we'd be very happy to have you and contribute to the discussions. And now I'm very much looking forward to questions.
Thank you very much, Astrid. So yes, we have 4 or 5 minutes per question. So I can already see one raised hand. So Charlie, please, you can ask your question.
Hi, thank you for the nice talk. I had 2 quick questions. You mentioned that when you have a rotating black hole and you regularize, you break spherical symmetry, but a classical curved black hole would not be spherically symmetric.
It's
right?
actually the horizon that is in the case of Kerr. So this image is probably helpful. The horizon in the case of Kerr is actually still independent of the polar angle. And in the case that we have here, the horizon acquires a dependence on the polar angle. So it's not the full space-time that is spherically symmetric in the case of Kerr, of course, it's just axisymmetric, but the horizon actually happens to be spherically symmetric in Kerr. And that's no longer the case in the regularized version.
So it's the independent of the axial angle.
Yes.
Okay, I see. I see. Also, I wondered, why is it that when you take the mass going to 0 limit near the singularity, or near where the singularity would normally be, why do you have to stay at the equator? Is there a reason why the equator is like a special plane?
Yes, so the equator is a special plane in Kerr, because in the Kerr spacetime, if you go to r equal to 0, you only encounter a singularity in the equatorial plane. So away from the equatorial plane, all curvature invariants stay finite in the case of Kerr. And so therefore, we definitely need our mass function to vanish fast enough in the equatorial plane, whereas if we go out of the equatorial plane, that mass function doesn't need to vanish in order for the spacetime to be regular.
I see. Okay, thank you.
Please, Bob.
Just curious, how big does this new physics scale have to be to see anything?
Yes, so the new physics scale would have to be quite sizable to see anything, right? So ultimately, what determines the size of the image features is something like the ratio of the black hole mass, or sort of the gravitational radius of the black hole, to the new physics scale. So if you put in something like the Planck scale, then you will definitely not be able to see anything.
But in a realistic case, how big does it have to be?
So I think you can turn it actually around, and it depends a little bit on the mass function. But if you actually look at cases like the Simpson-Visser mass function, then you can even use post-Newtonian constraints to constrain the mass function, to constrain the new physics scale to lie at, I think, smaller than 10 to the minus 5 meters, if I remember correctly. And if you actually want to have visible effects, of course, it depends on the mass of the black hole that you're looking at, how large that scale then has to be, sort of in meters or in any units. But you want this parameter, sort of the dimensionless parameter that is formed by the new physics scale and the mass. You want that to be of the order of sort of 0.1 to 0.5 or something to see effects. So this is sort of, if you make the assumption that the only modification comes in from quantum gravity, then at least for these cases which have lower spin, you will not be able to see anything. if you make the assumption that effects have to set in at horizon scales, for instance, because of the information loss paradox, then you can really use these observations to test. Right? And of course, you can also make the assumption that it's not quantum gravity that regularizes black holes. Maybe there is just some classical modification of gravity, in which case you don't have any theoretical argument at all to tell you something about the scale. And this is then a way to get observational access to that. But certainly if you take sort of the view that the only modification of gravity is quantum gravity at the Planck scale, then of course astrophysical black holes don't have any chance to ever see any effect.
Okay, so it is perfectly 40 minutes. So maybe Shinji, if you can ask quickly your question. Yes.
Yes. So do you have a dictionary between your parameterized solutions and the solutions in concrete theories?
We don't have that because we have not been looking at dynamics, but for some of the regular black holes, in particular in the case of spherical symmetry, there are of course solutions in theories beyond GR. So where there is, for instance, additional charged matter present or things like that. But currently we're working at a sort of more effective level. But ultimately, of course, it would be great to have a sort of dictionary that says a bunch of fundamental theories lead to a bunch of particular families of metrics, and those lead to particular image imprints. We have sort of worked on starting with the family of metrics and understanding whether there's any way to connect particular image features to particular principles.
I see. Yeah, thank you.
Okay, Astrid, thank you very much. For sure, we can have more discussion during the discussion session.